Hello, am I audible?
Yes, sir. Audible, sir.
Okay, thank you. So let me just start. Maybe some other people might join later on, or they can just watch the video lecture anytime. Okay. Okay, so what we are going to do today is a little bit start from what we left, where we left from last week, and then we are going to transition into the questions of the week four, or as per that NPTEL program, it's week three, but which includes some of the problems based on the carrier transport and how the electron and hole pairs are generated in presence of the light or any other external source, and how the electrons and the holes move inside the semiconductor, what how the charges play a role, and how the electric field is developed inside the electric field inside the semiconductor. So I'm Shahzan Butt, and as per the protocols, we have to introduce ourselves every time. So I'm Shahzan Butt, and I'm a direct PhD student at IIT Bombay, and this is a introduction to semiconductor devices course offered by IIT Hyderabad and IIT Madras in collaboration. And it's taught by Professor Naresh Imani from IIT Hyderabad. And if you have any queries anytime, you can just reach me by this mail. Some of the queries I have received over the some over the mail, as well as uh, the Google group we have, where all of the students are present. So, without just wasting our time, just we will directly jump into where we left. Okay, so let's get started. So, this is the page where we left last time, and if you remember, we derived how the band structure comes into picture. This is the band structure, something called as EK diagram, E versus K diagram, or it's also called as dispersion diagram. Dispersion diagram. Why dispersion diagram? Because it is similar to what happens in case of waves. So dispersion is a wave phenomena, and different frequencies, different waves travel with different frequencies. They mix with each other, they interfere with each other, and gives rise to a new wave. That is the dispersion, and that's why it's sometimes written as omega versus k. Don't get confused with it. Some people write it as E versus K, but you can anytime write E as H bar omega, which is the energy, and you can write it as omega versus the K, which is the wave vector. And this particular K is actually under root of kx square plus ky square, and in if there are two coordinates. So it's a and why I'm not showing the third coordinate is because you cannot draw a four-dimension plot on a 2D paper or wherever you write your plots. What I'm telling is that if you have, let's say, a kx direction, you have ky direction, then you can show energy direction in this axis. You cannot draw a fourth dimension in this because at most we can show this three dimension on it. Otherwise, in actual sense, it is kx, it is ky, and kz, and then there is energy. But what we are dealing with actually is that we want to show it visually. That's why most of the band structure plots you might see that is a three-dimensional plot. Two of these dimensions and one is the energy dimension. So that's why you get a plot something like this, which is a kind of something called as paraboloid in actual three dimensions. Okay, so that is just a brief thing about it. Let's not kind of deviate from the topic. So where we left is that we got a band structure and the reduced zone representation. So the reduced zone representation, where we have kind of we are only dealing with this particular zone where the where this point is called as something called as gamma point, this point is called as X point, and these represent directions in different Miller indices. That's what we discussed last time. And there we have one band, there is another band, there is one more band. Most of the time the electrons are filled, this particular band is filled with electrons. These are the innermost electrons, and they don't take part in conduction. Not take part in conduction. And these particular bands also contain some of the electrons, and if you kind of hit it with some kind of, let's say, photon, some of the photon, or as well as some kind of external perturbation. Perturbation means some external force that's going to give the energy to the electrons to get to the higher energy state. And this can go here, and you have a vacant site here, and now the conduction can happen. This electron can move freely. This is the conduction band. This is the valence band. This vacancy we call as hole. This electron, this particle we call as electron. So we have electron hole picture. So that is what we developed from the basic solving the chronic penny. We went into the band structure, and we went into how the electron and hole takes place. So we went from this particular thing where we had the consider the nucleus, the atoms, then we approximated it with this particular Wells potential. Then we solved something called as chronic penny model, and we used something called as Bloch's theorem, which uses the periodicity of the lattice, and says that the potential at x plus a is exactly equivalent to potential at x, and the wave function at x plus a is equivalent to wave function at x, but with certain e to the power I k a term. And we use this particular thing to derive the fact that we have the certain allowed states, and certain not allowed states. And we got the equation where there is some term on the left hand side, where there is some term on the right hand side. This term is something like cos of k, and here you have some terms like sine hyperbolic of k, and so on and so forth. You cannot solve this equation because this is an implicit equation, so you solve it graphically. You plot the left hand side, you plot right hand side. When you plot both of them on the same axis, the right hand side is cos k term, so that sets the value to between plus 1 and minus 1. So the overall things cannot go beyond plus 1 and minus 1. And when you draw the left hand side, you get something like this. And we saw that these particular levels are the allowed energy levels, and in between you have not unallowed energy level, no, those energy levels which are not allowed. So these energy levels are not allowed because this particular value goes beyond minus 1, and this is not accepted as per the equation. Okay. And when we draw this particular figure in zone representation diagram, we get this is extended zone representation diagram. We draw this, we get these bands. We get these bands where this is the energy gap. Now we what we do is that we don't want to kind of work in this extended zone representation. We want to simplify it, so we went to reduced zone representation. And what we get is that we fold these bands back into the first, something called as first Brillouin zone, which is right here. And you get this particular, you fold these bands back, you get these particular curves, something like this, so on and so forth. This is the first Brillouin zone, this is the first Brillouin zone. All right, so this is the overall kind of flow from here down to here, then we would get these bands, then we get extended zone, then we get the reduced zone representation. And now we play with this reduced zone representation, and we don't consider these for conduction because they are the electrons here are tightly bound with the nucleus. They are not kind of they don't play a part in conduction. They are not as such free electrons. So the electrons of our interest lie somewhere maybe here. When they go here, they can play a role in conduction. So we call the minima of this as We call the minima of this as conduction band, the maxima of this as valence band. And that is how we get the, let's say, something called as band diagram. So we are mainly associated with these points, okay, at k equals to 0. So this particular point is called as gamma point, where the k is equivalent to 0. And that's what we mainly show in something called as band diagram, where this is EC, this is EV, this is the, let's say, intrinsic level. And what if the electron is, let's say, here? So it's something like this. Its EK is something like this. It is at this place in parabola. So whenever you try to apply the electric field, just like, let's say, if we apply the electric field in this direction, let's say we have applied the electric field in this direction. So what is going to happen is that these bands are going to bend. So because you have applied certain electric field, so electrons are going to respond. So let's say if the electron is here, the force applied on the electron is minus QE. So it will be opposite to that of the electric field. So it will go in this direction, let's say. So what is going to happen is that when the electron goes in this direction in the EK space, there will be kind of a motion of the electron in the EK space itself. That is that is what we will be dealing right now. And how that motion translates into E versus X space is something like oscillatory signal. But that's a different point. We don't want to kind of go into that details. But I just want to give you some little bit basic and overview about how this picture comes into this. So that's what we are going to deal about. So when we have this EK diagram now, we're starting from this point. We have this EK diagram in the first zone, Brillouin zone. This is k equals to 0. And you see this particular thing is the first Brillouin zone. And when you draw this particular band, which is E versus K, let's say you have an electron here and you apply certain, let's say, field in this direction. So F is minus Q times E, so the electron is going to go in the opposite direction in the EK space. An electron goes here, but what happens when the electron reaches at this point is that it faces a similar type of situation. It faces a kind of, I should say, it reaches the zone boundary. This is something called a zone boundary. So this is zone boundary. So it reaches the zone boundary, and it is like that if electron reaches this thing, it is equivalent to that electron has gone at this position, or electron has reached this position. It's just like electron reached this position, it appeared back at this position because of the symmetry of the lattice. Okay, so it is hard to imagine, but you need to understand it because the lattice is symmetric. We are considering the symmetric lattice. So if the electron goes up this particular goes up this particular EK particular parabola, so it reaches here and it kind of goes into the other unit cell. But it's as if that particular electron appears here because of the symmetry. You can show all of these things in a single parabola because you have folded back all those unit cells into a single band here, into a single zone, which is the reduced zone representation. So that's why it's kind of due to symmetry, electron appears back here. Now that particular oscillation happens for the electron around this parabola when there is an external field present. Okay, so electron always wants to go up opposite to that of the field, and that's why the electron wants to go here. It reaches here, it appears here, and this oscillation goes back and forth, back and forth, back and forth. And now the question is that this oscillation is, we are talking about a pure crystal where there are no impurities present. And what does impurity do? These are defects. They kind of scatter the electron. Scatter means they randomize its momentum. Randomize momentum of electron. So let's say what happens is that if electron goes here above due to electric field. And what happens is that if there is a scatterer present here, scatterer can be anything. It can be a it can be a dopant, which is a doping atom. Any foreign atom can be a scattering agent. It can be ion, any ion. It can be a positive charge. It can be a negative charge. It can be impurities. What happens is that electron interacts with the scattering center and due to many types of interactions, let's say Coulomb interaction or any kind of electrostatic interaction, electron is not able to kind of follow its original path that is going above the parabola. It just randomizes its momentum. It goes here, then hits here, comes back, it electron then goes here, and it goes here. So it's a kind of totally randomizing its momentum, because you know that the crystal momentum is h bar k. So what happens is that because of the electrons interaction with the impurities, its momentum is totally randomized. Let's say it was having some k1 value here, then it goes to here with k2 value, then it comes back and the k value keeps on changing. But that happens because there are impurities present inside it. Okay. So that is why this particular scenario of something called as block oscillation, it is very difficult to see experimentally, or even I should say not, even if you have the purest of the devices, then only you are able to see it. Otherwise, this block oscillation, which should have happened, because that is what EK diagram tells us. Whenever you apply a field to the electron, it's going to oscillate in that particular K. But because of the impurities, because of the scattering centers, the electron is not able to do it. Okay, now what happens is that if you, let's say, let me rub this thing, or let's keep it like this. What happens is that let's follow this particular thing. Let's follow this blue curve here, this parabola. This parabola is E versus K. And now if you want to, let's say, compute the velocity of the electron, which is something called as group velocity. Okay, that is equivalent to d omega over dk, or I should say d 1 by h bar d dou e over dou k. That is the slope of this particular parabola. That is something called as group velocity. And group velocity is just like, it is the velocity with which wave packet travels inside the solid. That is the actual velocity with which the electrons travel inside the solid. It's not the, I should say, the drift velocity or the thermal velocity or the diffusion velocity, something like that. The group velocity is the actual velocity with which electron travels whenever the external force is applied to it. And why that is the case? Because if you see, let's say, let me just insert a page here. So let's say if you think about this thing, if you have a if you have EK in the reduced zone, something like this, you have this parabola, and this is K equals to 0. What happens is that electron is like a wave function. It's like a wave function. Or rather, don't confuse this with the wave function term. It travels just like a wave packet, and wave packet looks something like this, with certain kind of spread of that particular packet. Basically, it shows the probability distribution of the electron. Now, this particular wave packet, its spread as well as the frequency, it depends upon the wavelength. And you know that there is a relation between k and wavelength. And this particular axis is k axis. That means at every point the k value is different, and that means at every point the wavelength of this is different. Okay, so that means if, let's say, in this direction k value is increasing, that means lambda is decreasing. Okay, that means this particular thing is decreasing. That means if let's say you have a wave packet of electron here, then as it goes above the parabola, k value is increasing. That means lambda is decreasing. Then it becomes like this. Lambda is the spread. Okay, if you have a, let's say, if you have a wave, then this is the particular lambda in space x domain. And if you have this x, if you have it in time domain, then this is called as something called as frequency. So as you go above and above, this kind of increases in frequency. So that happens on the other hand. Let me just show the wave packet as a simple sign. Maybe you might be able to understand with that. Okay, just If you consider this to be a wave packet, then as a wave packet goes above, it becomes like this, it becomes like this, it becomes like this. On the other side, it also becomes increasing kind of frequency. So that is how the wave packet travels. So it is as if the k is increasing, the lambda is reducing, and the frequency is increasing. Frequency of this particular wave packet in time. And what is happening is that all of those wave packets, they kind of mix together, and it gives rise to a, I should say, when you kind of have certain frequencies, with let's say this is frequency f1, this is frequency f2, this is frequency f3, this is frequency f4. When you combine them, you get a totally different kind of let's say you can get a different type of a wave where you have the something like the envelope, and you can have something called as this particular thing, which is called as the carrier. It comes simply from the kind of wave mechanics. There is no, you can just simply understand it from the Fourier series. So if you have many of the frequency components together, then you can just apply the Fourier series. And just like, for example, if you have a sine wave, let's say, if you have a sine wave that is going from minus infinity to plus infinity, this is a sine wave, then it has only one frequency component, which is omega naught in frequency domain. But if you have a sine wave which is time limited, let's say this is from 0 to t naught, then there is a particular spread of the in frequency domain around that omega naught frequency. Okay. Why that spread comes up is because, for to make this signal, to get a time limited signal, you are actually adding infinite sine waves of different frequencies. You are adding this sine wave to this sine wave to this sine wave to this sine wave, and you are adding so many infinite components that you finally get a time limited signal, which is limited by this 0 to t naught. All other components which are here and which are here, they get cancelled because of interference between these other components. Okay, that is the concept of the Fourier series. Similar thing happens with the electron, because electron is traveling with different frequencies and different waveforms. So that is what happens, is that now we consider the electron to be a wave packet, and it has something called as group velocity, it has something called as phase velocity. Okay, so what happens is that there is the group velocity is determined by the slope of this EK diagram. How this comes up, it directly comes from the fact that energy is h bar square k square divided by 2 m. You can just write it in terms of let's say you can write the energy as energy, and you can actually use the Newton's equation, simple Newton's law, F equals to ma, to arrive at this particular thing, how the group velocity comes. And it simply comes from the classical mechanics. There is no quantum in this thing. And but the beauty of this thing is that it gives us this particular relation, that the group velocity, it's the velocity with which actual information, or the electron at this particular thing travels. Okay, there is this particular thing, something called as envelope, then there is particular thing this called as carrier. So there are two different velocities. That's why there are two different velocities. One is the group velocity, other is the phase velocity. Phase velocity is at which the velocity at which the phases vary, and most of the time you will see phase velocities most of the time greater than the speed of light. And don't get confused with it, because phase velocity does not represent the actual information with which it is traveling. It has a very deep explanation. I don't want to go into that detail, but you can just look for it. It has a very deeper explanation why this is greater than group velocity. But the concept is that as the electron goes like this higher and higher, it changes its k. As a result, it changes its wavelength, and we have a concept, something called as group velocity, with which the wave packet travels. Now we talk about wave packets. Wave packet looks something like this, where this particular inner thing is the wave packet. Okay, so this is just like an kind of inner thing. Let's say let me just drop it. So you have something like this. This is a wave packet, and why it's formed is because you know that electrons are traveling with different frequencies along this particular curve. Now, what happens is that if you just simply kind of want to find the group velocity of that particular electron, you find the derivative of this parabola curve, of this curve, and that is why when you differentiate this curve, you get a curve something like this. Why? Because the slope is maximum here, so that's why the slope is maximum. And the on the other side, slope is maximum in the it's a negative slope, so you get a maximum point here. So this point, so this point. So this is the group velocity of electron, which is 1 by h bar dou E over dou K. Okay. Now, this means that electron reaches its maximum velocity at this somewhere in the middle of this band, and then its velocity starts to decrease, and by the end of this, its velocity almost kind of becomes this curve says that its velocity becomes almost zero, and that is a kind of ambiguity, because if the velocity of this particular electron will become zero, the group velocity, then how is it going to move inside this particular lattice? That's why I told you that this particular scenario is just for one region, something called as Brillouin zone, first Brillouin zone, first Brillouin zone. And the concept that I told you, that electron, it is as if electron disappears here and they appears here. That is what makes electron to travel. Because we are showing it in a reduced zone representation, we're not showing it in an entire lattice. So whatever is happening in the other cells, that is happening in a single cell. So that is basically the concept of why this thing is happening, even the disappearing and appearing of the electron, as well as the group velocity. Okay, now what you have is that if you want to find something called as effective mass, you might have studied that you can compute effective mass. Again, this can be computed from simple Newton's law. You can compute effective mass to be equal to h bar square d square E over dk square. So this particular thing is something called as curvature of the EK diagram. Okay, and when you compute the d square E over dk square, you get band something like this. You get something like this. Okay, these are d square E over dk square. This is the effective mass. That means what happens is that it is as if as the electron is going higher and higher to the in the parabola, its velocity reaches maximum and its mass almost becomes infinite. This is the asymptote almost, I should say. These are asymptotes. These are not touching the axis. So it becomes kind of a heavier and heavier as it goes up above this parabola, and that it's kind of just like the electron's motion gets impeded as it goes above and above this parabola. But again, because of why the electron does not reach this point is because there are impurities at other states, and because of the impurities, electron hits there, it goes here, and it keeps on moving inside the Brillouin zone, okay, inside that particular lattice cell. So that is the overall concept of this EK diagram. It is a little bit confusing. I know, I can understand, but it is difficult to imagine how this particular thing is happening, because all of this thing is happening in three-dimensional crystal. And what we are showing is the single unit cell. Let's say the concept of Brillouin zone is actually a very, I should say, if you have, let's say, lattice points like this, these are the atoms, then how you draw the Brillouin, how you consider the first Brillouin zone is something like this. This is the first Brillouin zone in a crystal lattice. You draw these perpendicular lines and the other perpendicular lines, and the single atom surrounded by these perpendicular lines is the first Brillouin zone. So whatever you're showing is happening in this particular unit cell. No, I shouldn't say unit cell, it's happening in this particular cell. Okay, and this particular point is something called as gamma point. If you go in this direction, this is called as X point, this is called as M point, this is called as R point, and I'm just showing this in 2D. So this is this is this direction, this is this direction. Now consider this in 3D. Now consider this in 3D. Now you will get confused to how to imagine. Okay, now then those Miller indices actually come into rescue. Okay, so what is happening is that we want to simplify whatever is happening in a crystal. That's why we are just kind of restricting our maths and restricting our theoretical explanation to this particular cell. And we are using the fact that because of the periodicity of these particular atoms, whatever might be happening with the electron in this cell, that might be happening here. That might be happening here. It's a very crude approximation, but that is what happens. That's a very, I should say, a very good approximation, at least to understand what is happening to the electron. But the only single thing we are neglecting here is that we are not considering any impurity. And if you consider the impurity, that is how the electron kind of moves inside this particular thing. Here, we are not considering any impurity, but there are impurities actually in the atoms, and electron gets scattered because of that impurity. And that is the concept about it. Now, if I talk about now, for example, the let me just see. Okay, let me just briefly talk about density of states. Maybe this thing is not necessary in the okay, but okay, let's go on to now occupation of states. Now we saw how the EK arises. Now we have to see how those states are occupied. You have the EK now in the let's say in the we are in the first zone. Let's say you are in the first zone. You have the E versus K now. Now there are states, many states present here, and you want to calculate those states. You want to compute those states, or you want to see how many states are there, how many states, and you want to see how many states. If you consider 1D lattice, 2D lattice, 3D lattice, you want to see how many seats are available for the electron to stay. Okay, so that is what is something called as density of states. But that's the next topic. So the first topic will be first concern topic is something called as occupation of states. Occupation of states tells you how these states are kind of filled and what is the probability that an electron will be at this state. All right. So and since we have so many electrons, there is not a single electron in it. Let's say if you have a single silicon atom, then the number of electrons is equivalent to the atomic number, and you can get you can simply consider how many silicon atoms are in a centimeter per centimeter cube, and then you can compute how many electrons will be. Let's say it's of the order of 10 to the power 20 per centimeter cube of electrons. So that's a huge number of electrons in a centimeter cube, and you cannot just think about a single electron occupying a state. You have to use something called as statistics, and you use the statistical concepts to arrive at something called as probability of distribution. What is the probability that the states will be occupied by the electrons, whether it will be occupied or whether it will not be occupied? So there are three main distributions. Distributions means how the electrons will occupy uh, the energy levels, or what is the probability of occupying the energy levels. We have something called as Maxwell-Boltzmann distribution, the Fermi-Dirac distribution, and Bose-Einstein distribution. Mostly you guys will be dealing about these two in the semiconductor physics, and the Bose-Einstein distribution is not much talked about here unless and until you don't talk about bosons, in which there is something called as photon and you call something called as phonon. So these two particles are the bosons. These are not particles, these are something called as quasi-particles. Let's not talk about it. There are many other quasi-particles. But if you talk about fermions, of which electron is one, electron is a fermion having integer half spin, it is having plus minus 1 by 2 spin. What is that? Leave that particular thing. Leave this fermion term even. It's just a jargon. And if you talk about Maxwell-Boltzmann distribution, it's applicable to distinguishable particles. And what that particular thing is, we're going to see. Just like the gas molecules, just like the electrons in a metal in or in a degenerate semiconductor, you can apply something called as Maxwell-Boltzmann distribution. And how these distributions look like is, if you talk about the Maxwell-Boltzmann distribution, it looks something like e to the power minus e over kt. And if you talk about Fermi-Dirac distribution, it looks something like e to the power e minus e to the power minus e kt plus 1. If you talk about Bose-Einstein distribution, it looks something like e to the power minus e over kt minus 1. So these are quite similar distributions. But Obviously you can arrive at this particular distribution by using certain approximation, and also to this distribution by using certain approximation, but these are kind of distributions of the electron, and this particular distribution says how the number of electrons with respect to energy are distributed in energy space. Let's say Maxwell Boltzmann says that if you go higher and higher in energy, the number of electrons will reduce, and you have most of the electrons at lower energy. And that just makes sense. Electron does not want to stay at the higher energy state by itself. Anyways, if you kind of make the electron to go to the higher energy state, it will naturally decay to the lower energy state, and that follows the Maxwell-Boltzmann distribution. Even this is applicable to gas molecules, or you can apply it to free particles even under certain approximations. And then we have something called as Fermi-Dirac distribution. Fermi-Dirac distribution says that because electron is a fermion and it follows Pauli's exclusion. Pauli's exclusion. That means in a state you cannot put more than two electrons with same quantum numbers. All of the four quantum numbers cannot be same. That means N, L, M, and S. So these all cannot be same for the two electrons present in a single state, energy state. So that's why you get something called as, let's say, Fermi-Dirac distribution, that you have to you have to have a distribution something like this. If this is something called as probability of distribution, then this is the energy. At T equals to 0 Kelvin, you have something like this. That means above this particular level, sorry, below this particular level, electrons are there's a much probability of electron being found. And above this particular level, you have zero probability of electron to be found. And this particular level is called as Fermi level. That's how this concept comes into picture. It is a level set by particular this using this Fermi distribution concept, and we consider that above this particular level there is zero probability of electron, below this level there is maximum probability of the electron. And basically it is just like a maximum energy of the electron in a particular system. That is what the Fermi energy is basically. And you might have studied it somewhere. Maybe you might remember something called as chemical potential, something called as electrochemical potential. That is the similar concept as Fermi energy. This is particularly used in chemistry. They use the concept of electrochemical potential, and we have the same concept of Fermi energy in case of solid state devices. Now, how does the Fermi statistics comes into picture? I won't go into this detail. If you want to go, I will upload the slides, but this is not a kind of, I won't go into the derivation of this. It simply comes from the statistics using the combinations and how the states are filled. But this is the particular plot I want to show you, I think this was given in the previous assignment set also. So now I showed you how the Fermi distribution looks like, and this particular thing is, let's say you have this particular thing at T equals to 0 Kelvin. It is a perfect step. This indicates that all of the energy states below Fermi energy are filled, or they have the maximum probability of being there. Electrons have the maximum probability of occupying these particular states, and all of the states above here, they have there is very low or zero probability of electron being found. And this particular scenario is at T equals to 0 Kelvin. But what happens if you increase the temperature? As you increase the temperature, more and more electrons go to the higher energy state, and you can see that electrons go here. There is a not electrons, I should say, there is a more probability of electron being found at the higher energy state. Okay, and there happens to be a gap here, and that indicates that more number of electrons has the probability at higher states. This means more probability of electron at higher energy states now. So it has kind of smeared. Smeared means it has spread the Fermi distribution function. That means the temperature spreaded the Fermi distribution function. And now because the temperature increased, so the energy of the electrons increased. So there is more probability of electron being found at higher energy levels. That is the simple concept of the Fermi energy level, Fermi energy, or the Fermi distribution function. Now, and that particular energy level where there is a demarcation, the electron at 0 Kelvin, there is a maximum, the at 0 Kelvin, at the Fermi level, below the Fermi level, there is a maximum probability of finding the electrons. Above the Fermi level, there is zero probability of finding the electrons. That particular level is called as Fermi level. Or maybe you might have heard somewhere that the Fermi level is a level where there is 50% probability of finding the electrons. That again comes from this particular fact that at least half, there is a half probability. You can see this particular value is here actually 0.5. So this is the actual thing, that at exactly Fermi level, the probability of finding the electrons is one half. That means 50%. And what happens is that most of the people get confused with the concept, like if you have a conduction band, now if you have a valence band, and let's say you have Fermi level somewhere like this, then as per this particular definition, it says that there is a 50% probability of finding the electrons. That means there should be 50% probability of finding electrons here. But this is an energy gap. In a pure circumstances, you don't have any electrons here. Then there is a flaw in this particular definition. And the reason is that this definition is not alone sufficient, because this is just telling you what is the probability of finding the electron. It's not telling you the electron is there. For the electron to be there, first of all, there should be an electronic state. There should be an energy state. Electron cannot just go and sit here. That does not happen. There should be an energy state here. There should be states. It's just like if you have chairs in a classroom, these are chairs, then the student comes in and student can sit in any one of the chair. This particular chair is something called as density of state, and student can now go anywhere on the and sit on the chair. Let's say student came here and sit here. Now you can say that probability, let's say the probability of sitting of a student on this chair was 50%. Okay, that was already 50%. But let's say if there was no chair here and the probability was 50% still, but you cannot say that the student has sit here because there is no place to sit here. He is not supposed to sit on the ground, let's say. So that is the similar concept of electrons density of states and the Fermi energy, Fermi function. Although there is a 50% probability of finding the electrons in the energy gap even, or at the Fermi level, wherever the Fermi level is present in this scenario. But electron cannot sit there because there is no states available to sit. Okay, so that is the fundamental thing people get mostly confused about. Fermi f of e just tells you about probability. It doesn't tell you it doesn't tell you where electron is. Okay, it does not tell you where electron sits or whether electron is going to sit there or not. For that, you have something called as density of states. Density of states are like the seats available. If there are no seats, then just talking about this is not going to make any sense. When there are seats available, then you can talk about that there's a 50%, since there is 50% probability of sitting at this particular place. Now, if there is a seat available, electron can sit here. But if there is no seat, electron cannot sit here. That's why we transition into something called as density of states. So the density of states is number of states per unit energy per unit volume. So that's why the unit of density of states is it's the number per unit electron volt per centimeter cube. So it's per electron volt per centimeter cube. So this is the unit of density of states. So it says how many electronic states are available per energy per unit volume. And now you see that if you have now the conduction band, you have the valence band. There is a band gap here, and you want to know how many states are present between some E value. Let's say you have a EK relation like this, and this is K, this is E, this is let's say let's say this is some value dk, and you want to actually see, or let's say let's do something like this. Let's say the particular value of energy here is E, and the particular value of K is K value is K, and let's say you want to this particular width is dk, and you want to see how many energy levels are present in this particular region, particular small region dk. Then you are going to do simple calculation. This is just a calculation task. There is no kind of any complicated thing in it. You are just going to calculate states, numbers. You're just going to do the statistics. And now the calculation is greatly simplified if we consider the band edge to be nearly parabolic here. Why that is the case, that we will deal later on, but that's the thing I actually talked in the previous lecture, that these bands are not purely parabolic. They are somewhat like this. So there is this type of curvature at the ends, but we kind of consider them to be parabolic because it's easy to deal with this. You can directly write it as h bar square k square by 2m, but only if you approximate it with this orange curve. If you do not approximate, then you have to consider these particular things, and it's very difficult to model these particular things. There are different approaches. You can model this particular curve, the black curve, but for the simplification, we are going to consider we are going to fit this particular parabola where the region near the edge of the EK diagram is almost parabolic. So this particular region is parabolic, and that is the region we are mostly concerned with. We're mostly concerned with this particular region. Okay, and now you do the counting, just simple counting. If you just consider this particular region to be dkx, let's consider it in a one dimension, dkx, and then you consider this particular region to be some dE region, small energy region and small k region. Then what is going to happen is that the number of states present will be equivalent to the number of that will be equivalent to the length of this particular region, which is dk, divided by this particular factor, which is 2 pi over lx. Where this 2 pi over lx comes from? Again, it comes from, if you consider a lattice, if you have this particular length L in real space, this particular thing is L, this particular thing is this lattice constant. You go into K space, all of the things get inverted, reciprocal. So now these lattice atoms are spaced at L, and this particular thing is A, and now you have the distance between these two energy levels. What I talked about in the previous lectures is now it is something called as 2 pi by L Lx. This is the particular thing. Okay, so this is the, I should say, the difference between the two levels in a case space. Okay, and overall Lx will be equivalent to number of atoms times the lattice constant. That is the simplest thing. But what happens is that this is the overall dimension of that particular strip dkx divided by the single strip width, which is the single state, which is equivalent to 2 pi by Lx, and multiplied by 2 factor, because the 2 factor comes because you have to kind of consider the spin up and spin down states for the electrons. So if there is a single state, then 2 electrons can stay in it at max, and that's why this particular 2 factor comes. So you're just counting how many electrons or how many states can sit in here. So this factor comes that the particular state can actually have 2 electrons. That means let's say one is for the spin up and one is for the spin down. So when you solve this, you get something called as something like nkdk, and this particular thing is basically n times the number of sites times the k times the number of sites times the overall this particular width. And when you write this particular thing, when you just kind of do the maths, you just cancel the 2 and 2 terms, you get nk to be equivalent to lx divided by pi, which is the density of states in k space. And if you extrapolate it into others, this is the case of one dimensions, because you considered only this is the one dimension case, only along this dimension. Now you got this dimension and this dimension. That is something called as two-dimension case. You have states here, you have states here. You get something called as density of states in 2D. And here you got this length because that is the length of overall length. Now you get area in the 2D case and you get volume in the 3D case. And here you got dk because that was the only k. In 2D you get dkx, dky. In 3D you get dkx, dky, dkz. And for the two-dimensional case, you consider the density of states just to be like in the form of a circle with the radius k. And then you do the similar procedure, you're going to get the density of states in k space. Now you don't need to worry about these particular things. Maybe you might have studied the density of states in E space, but you can anytime go from E to K space. So just a representation. You don't need to worry about. You can just understand the concept and you can just go to slides anytime. Now what happens is that when you go from K space to energy space, you have to do the Fourier transform and you get the density of states in energy space, something like this, which is density of states of 3D is proportional to square root of energy. And this is for the 2D. Nope, this is not for 2D. This is for the 3D again. And you get density of states for 2D to be proportional to e to the power 0. That means it's constant, it's not dependent on energy. And you get for 1D case, it is proportional to 1 by square root of e. And these particular relations are important, that it says that if you have a three-dimensional system, then the density of states, that means the states available per unit volume per energy, is actually proportional to the square root of E. It's something like this. If you have density of states in 3D versus the energy, it increases like this. It's the square root of E relation. That means there are more and more number of states above certain energy, above certain energy. What this energy is, we will see. This is basically every time written with respect to some energy. Let's say this is E naught. So this particular energy is E naught. Okay. So you have more and more number of energy states above these particular things, above this E naught. And for the 2D case, this is constant. And for the 1D case, it is inversely proportional to E, something like if this is E naught, it is something like this. Okay. And for the 2D two dimensions case, for the density of space in 2D versus the E, it's a constant. Okay, at this particular E naught. There are constant number of states present at this particular these are the number of states. And now this thing is complicated thing. You don't need to study about this thing. Now what happens is that this is the important thing I wanted to show. And this will be the final thing, then we will jump to directly to what we are going to study. So what happens is that now we said, let's say we have a 3D crystal. We have a 3D crystal and we have density of states in 3D to be proportional to some square root of E. Okay. Now if you consider conduction band, you consider valence band, then this conduction band or this valence band can set a reference energy level for this density of states. That is what you measure the density of states or energy with respect to. Okay, so you can write it as E minus EC. That means you're going to measure it from here, or you can write it as, let's say, E minus EV or EV minus E or E minus EV rather. You can write it. So that means if you consider this, then you're going to measure it from with respect to valence band. If you consider this, then you're going to measure it with respect to conduction band. So every time we write this energy, we write always energy with respect to certain level, a fixed level, and and that's your choice whether you want to write it with respect to conduction band, with respect to valence band. You're going to get the similar results in the end. But these particular values are just going to set a level above which we are going to see how many states are available. Okay, so in that context, this should be actually EV minus E. Okay, so now what happens? Now the important concept is that you have, let's say, density of states. We're only talking about 3D right now because we're talking about a three-dimensional crystal, let's say silicon, maybe somewhere like a diamond-shaped type of a crystal where there are atoms like this, and we're talking its number of states available per unit energy per unit volume. And we saw that if this is conduction band H, it increases like this as a square root of E minus EC. This particular this is a particular energy axis. Okay, so what happens is that if you now consider this was density of states. Now you draw on the same plot the Fermi function, which gives the probability. It's the distribution function. Because that Fermi function is also drawn with respect to energy. But let's say we draw it as T equals to 300 Kelvin for the silicon. Okay, so it looks something like this. It looks something like this. All right, where maybe I just extrapolated it. Maybe it looks something like this. Where this particular maybe let's consider this to be a Fermi level. Okay, and that means Fermi level is quite close to the conduction band. And that means the red region is the probability of electron being occupied. Now, what happens is that you know that somewhere here there might be not here exactly. Let's say on this end there is valence band also, and this particular thing is the band gap of semiconductor. Now, how you compute the electrons in the in this particular system is by considering both the f of e and g of e. That's what is the main concept. You don't have to only consider the Fermi distribution function to check how many number of electrons are present. That is the partial information. That just tells you the probability. And rather just only considering the density of states is not going to give you complete information, because if you remove this thing here, then the density of states just tells you how many states are available. That means how many seats are available. It does not tell you how many electrons are there. And if you bring back the Fermi function, and if you just kind of remove this thing, it tells you what is the probability of finding the electrons, not how many electrons are present there. But it is only when you consider both of these that you get information about the number of electrons. Now you get number of electrons with respect to energy that is equivalent to probability of finding the electrons multiplied with the states present. So how many seats are present and what is the probability of electron to sit in that seat. And what is the probability? That means Fermi function times the density of states. So this is the number of electrons in this particular system, how you can compute. That means you have to multiply these two regions, and when you do so, you get an overlapped region, which is like this particular thing, where these two curves intersect at this point. That means this region is common. You have multiplied these two particular curves, you get this region. This particular region is showing you the number of electrons. This is showing you the number of electrons, n of e. It's a number of electrons as a function of energy. Okay, and what it is telling you is that at certain energy value, the electron will be maximum. There will be maximum electrons present, and as you go higher and higher in energy, there is a very weaker chance that you will find an electron. This is this tail. You see this tail of this exponential. It's like exponential decay, and that's why this tail is sometimes called as Fermi tail. It's a very high energy tail. It's a high energy tail. That means if you have sometimes high energy electrons, they will be residing here. If you have low energy electrons, they will be residing here near the conduction band. But if you excite them more, they will go to here, this particular region. But This is the overall distribution of the electrons already in that particular system. It is not that we are externally exciting them. It is these are the electrons already present here. This is the distribution of electrons overall present in the semiconductor, present above the conduction bands when you kind of excite them over the conduction band. This is how the electrons are distributed. But you see that there are very few electrons at higher energy. More of the electrons are localized in this region. Okay, but these particular electrons are very high energetic and they are there available there. And now we are going to see in the slide that how these electrons play a role and what kind of role they play in the devices. Let's say PN junction device or BJT or any kind of transistor. How these type of electrons, which are the hot electrons, these are something called as hot electrons. Hot electron just refers to the kind of energy of an electron. It's very high energy electron. It's something called as hot electrons. That is the number of electrons with respect to energy. Now, what you do is that if you want to count the electrons, this particular thing was shown, this particular region here was showing you the number of electrons distributed in energy space. Now, if you want to count how many electrons are there, count, then you can simply integrate this curve. You can integrate this curve with respect to energy. You can write number of electrons to be integral of f of e, g of e with respect to energy. And if it is with respect to energy, that means the limits will be from EC, from this particular region to infinity, to all of the above energy levels, to infinity. This is the total number of electrons. This is the total electrons, number of electrons. You can compute by integrating this particular curve up to infinity and you get the total. This will give you a number. This will give you a number. Okay. This gives you a distribution of electrons, not a number. It's a function of V. All right. Now, what happens is that if you let me just take this thing from here. To here. Okay, let's insert a page. Now, what happens is that if you kind of have this picture in mind now, you have this picture in mind, then let's say you consider something called as PN junction diode, PN junction. And first of all, I want to just show you that in a energy band diagram how this looks. You had EC, you had EV. You make density of states like this, like this. This is density of states, and there is Fermi function also. So when the Fermi function intersects the density of the states, you get the energy distribution of electrons like this, like this. These are the electrons, energy distribution above the conduction band. So there might be there is a Fermi function above here. So there's something looks like this. So this particular region is the number of electrons. And the similar thing is in the bottom side. You have a density of states like this, and you have a region something like this, where there is intersection of the Fermi level, and you have something like this. These are the holes distribution. Let's say write it as P of E. This is the distribution of the holes below the valence band. This is the distribution of the electrons, electrons above the conduction band. And now you see that it naturally tells you as you go higher and higher, you get a very low chance of finding an electron. As you go lower and lower, you get a very low chance of finding a hole. Okay, this particular energy, when you draw it, this is actually with respect to electron energy. And this particular x is x-axis. This is a spatial coordinate. So this particular thing, if you have in mind, then what we do is that when we, let's say, go from this particular picture is for a semiconductor chunk. If you have a simple semiconductor sample, you have conduction band, you have valence band, and this type of distribution follows. Now, what happens is that you go from a semiconductor, one semiconductor piece to a two semiconductor pieces. You make something called as p-n diode. You dope this side with acceptors atoms. You dope this side with donor atoms. You get to something called as p-n junction diode, where there is a junction or something called a depletion region formed here, and there are positive charges with electrons, there are negative charges with holes. Electron wants to go from this region to this region, hole wants to go from this region to this region. Equilibrium is set up, and you get a band diagram. What is a band diagram now? Let's transition into that. That will be our transition into the assignment. The band diagram comes from this picture, band diagram. Oops, band diagram. This is E versus X. Don't confuse with band structure. I'm just emphasizing on this point. Band structure is E versus K. Band diagram is E versus X, E versus space. When you had a single chunk of semiconductor, you draw the conduction band like this, valence band like this, and let's say intrinsic level or Fermi level was in the middle. Now you have two samples. You have P type, you have N type. This is before joining. This is before joining the samples. You have p-type, you have n-type. Now, how the band diagram of p-type looks like, it is something like the Fermi level is near the valence band, showing that there are more number of holes in the system, and n dot p equals to ni square. You can compute n as ni square divided by p. If let's say p is equivalent to 10 to the power 17 per centimeter cube, then you can get n as equal, and if ni is equivalent to 10 to the power 10 per centimeter cube, intrinsic concentration is the background concentration, which was already present, the background number of electrons and holes. So that was already present inside the system. That was already present here. Before it was P, before it was just semiconductor, so there was intrinsic concentration. Then you doped it with Na, you got you got more number of holes, and that surpassed this Ni, and you got 10 to the power 17 number of holes. Now you get n to be equal to 10 to the power 3 per centimeter cube. That means there are 10 to the power 17 per centimeter cube holes and 10 to the power 3 per centimeter cube electrons in this side. And similarly, you draw a band diagram over here, you get a Fermi level somewhere here. The the energy gap of both of these is similar, same, because it's a semiconductor sample. And you get EC, you get EV, you get EF. The Fermi level is close to the conduction band here. It's close to the valence band here. That means this is N-type doped with ND. This is a P-type doped with Na. Now you combine these two regions, and from the basic things you might have studied from it, what happens is that because the Fermi energy is higher on this side and Fermi energy is lower on this side, that means the electrons on this particular side, on this particular region, they will kind of move to this region, diffuse to this region because of higher energy, Fermi energy. And while doing so, you it the we say that we can also say that the holes will move to this region. That is a similar picture. The electrons move this to this place, the holes will move to this place because because once the electron will move from this region to this region, holes will be created here. That is the same picture. Okay, so while doing this, what happens is that the this particular level shifts down and this particular level shifts up because the Fermi level wants to be aligned. Fermi level wants to be aligned, wants to be aligned in equilibrium because electrons and these holes cannot go move on forever. There has to be equilibrium reached. The number of electrons going from this side to this side should be equal to the number of holes going from this side to this side. Let's say two electrons are coming in from this side, there should be two holes going to this side. And while doing it, the Fermi level gets aligned. That means that there is a common Fermi level now, which is something like this. Common Fermi level, EF, and what happened is that because this particular band moved down and this moved up, so you see that this is up, this is down, but it remains p-type here. The Fermi level in the p side is near to the valence band, and it moved down here. That means it's here, and this particular band is here. This is the conduction band on n side, valence band on n side. It is near to this side. That means this region remains n-type in the bulk. But in between here, there is a bending. The energy level bends, and this is the overall band diagram of the particular p-n junction, what you might have studied. And this particular region is the depletion region. And this is something written as WD, which is the depletion width. Depletion width, and it can be computed approximately by 2 epsilon over Q, 1 over NA plus 1 over ND, V built in plus minus V applied. Now what these particular things are, we will talk about. But Na and Nd are the doping, epsilon is the permittivity, Q is the electronic charge. This just comes from simple electrostatics. You will see. There's nothing much complicated here. This is a built-in voltage which is developed after the potential after the space charge region is formed. So what happens is that when the electrons move to this region, holes move to this region, there are ions left here, immobile ions, and because of that, electric field is set up in this direction. This is the electric field, and you know that you can write electric field to be equivalent to some d dou v over minus dou v over dou x, and you can whenever you do the computation for the case of silicon, you get built-in voltage to be approximately equivalent to 0.7 volts. That is the inbuilt particular voltage developed in that particular junction, which stops the electron from going from n to p side, and then stops the hole from going to p to n side, and that is what maintains the equilibrium. And you're going to see that this particular electric field gets changed, as well as you can change the depletion width as you change the applied voltage to this device. Till now we have not applied any voltage, so this particular thing is nothing here. We have not applied any particular voltage here. This is just when the two silicon chunks are combined, joined together. Now what happens is that now there is a more kind of, I should say, important picture. This at this page. So now you have this thing here. Let's take this from here. Let's copy, duplicate it. Let's place it here. Oh, let's remove this. Let's remove this. And now from the earlier picture which I showed here, this particular picture of understanding the distribution of electrons, I will apply the same picture in the diode and show you how this particular conduction takes place. So what happens is that if you draw the n of E, which is equivalent to the f of E times the density of states on both of the sides. Okay, you have a distribution here. Now I am drawing only n of E, which is this distribution, multiplication of Fermi function and the density of states with this particular tail, Fermi tail, which it's a very high energy tail. So high energy electrons are present. It's a very exaggeration. So it is something like this. Okay, yes. So this is showing this particular thing is showing the energy, and this particular axis is showing n of E, number of electrons with respect to energy. And similar happens to that of holes. Let me draw the holes with different colors. This is a hole distribution. And this is P of E. Let's say in this direction and in this direction is energy. That means as you go higher and higher, there are very few holes present. As you go higher and higher, there are very few electrons present. More of the electrons are here. Now you see what happens is that it's a similar thing on this side. If you kind of take this particular thing, duplicate it, it's on this side again. And if you duplicate this thing, uh, this is on this side again. This is n of E and P of V, the distribution of electrons and the distribution of holes on both of the sides of p-n junction. Now what happens, just see, once this depletion region is formed, it sets up a barrier between the electron distribution on one side and electron distribution on the other side. And what is going to happen is that now if any electron wants, let's say if any electron is here and it wants to go in this direction, then it cannot just simply go because there is a high energy barrier present here, which is this barrier. It is just like hill, electron wants to go uphill, but it cannot go by its own. Okay. And the main concept I want to highlight here is that this particular distribution, this particular distribution, this is telling you that if you draw a level, if you draw this level here, which is this particular mountain point, mountain peak point, it means that up to these particular number of electrons, up to this energy, these electrons don't have a chance to go above the hill, don't have chance to go above hill because they are below this hill energy. If this is hill and this is these are the number of electrons, they are below this, below the energy of this hill, below the kind of potential energy of this hill. If they have to move above the hill, they should be having very high energy so that they can just surpass the hill. And which electrons are having high energy as per this electron energy distribution? They are these electrons which are in the tail. You see that they are above this dotted line. And these electrons can move to the other side of the junction, even if there is a barrier setup. Okay, but there are very few electrons. It accounts to something called a leakage. Okay, and this happens all the time. There are very few electrons, but they are very high energetic electrons. And this, why they are high energetic electrons? That is set up by the rules of nature, the density of states and the Fermi function. They are both set up by a kind of inherent distribution of the electrons inside a crystal. We don't do anything with the how that particular thing sets up inside. That is set by the nature itself. Now, what happens is that, but there are very few electrons here, and as such, we say that the overall kind of current in the off state is zero. There's I mean you cannot have any let's say electrons. There may be few electrons going from this region to this region, and there may be few holes going from this region to this region because there are few holes present here. Similarly, above this region, because for the hole the barrier is this particular region. This is the barrier for the hole. This is the barrier for the hole. And now what happens is that this is without bias. Without bias, we don't apply any external voltage. Now let's apply the external voltage. Let's take this, duplicate this. Okay, now let's apply the voltage. Apply voltage. Now, what type of voltage we want to apply? We apply the positive to the P side and negative to the N side, something called as forward biasing it. When you apply the voltage in a forward bias region, what you are doing, let me drop this, let me drop this thing, let me drop this thing. What you are doing to the bands, you are just moving them up and down. That's it. The rest of the job is done already because the electron has its energy distribution. It is just like it's just like you have you have a barrier between the two water levels, and you are just modulating the barrier between these two water levels. If you want the electron from this side to this go into this side, you are lowering the barrier, lowering this barrier. And if you want to block them, you will increase this barrier because electron already has this energy inside it, energy distribution. You are not doing anything to it. What you are doing is that you are just modulating the barrier. When you are applying the voltage now, you reduce this barrier. In the pink curve, I will show how the barrier gets reduced. You apply the positive on this side, this gets reduced to this. Okay, let's not overlap it like this. For the biased case, you have something like this. You reduce the barrier, but the electron was already having a distribution like this. So now more of the electrons are above this region. There are more electrons coming into picture. Now those electrons will move to this side. Similarly, more of the holes are above this region. Now those holes will move to this region, and it gives rise to a conduction process. You are just modulating this barrier. You are just modulating this particular barrier here, this thing. That's it. You're not doing anything else. That's what the voltage is doing. Voltage is either bringing this barrier up or bringing it down. That's it. Bringing it up or bringing it down. We are considering this to be grounded and negative. You are considering this to be attached to positive. This will bring it down. This will bring it slightly up. And when it goes up, the electrons here, then the dotted line will shift now to a place something like this. When it shifts, more electrons are coming out. More electrons are present at higher energy level now. And these higher energy electrons will definitely try to move above the barrier, they go to the other side, and that is how the conduction takes place. And in a reverse bias case, the opposite happens. And what happens in the reverse bias case is, okay, I got this thing. What happens in the reverse bias case is iska ulta. So when you apply the reverse bias, you apply the n negative to n side and positive to p side. You are increasing the barrier so much so that the electron distribution, even if there was hot electron present in the Fermi tail, now that is still below this level. Now these electrons cannot go on to the other side. Similarly, the holes distribution was present like this, but that is still below this level and the hole cannot go here. Similarly, the electron present here cannot go above the barrier. So this is the reverse bias regime. And a diode in a reverse bias regime acts just like an off switch. No conduction. No conduction. And you have just seen it because you have increased the barrier so much so that now the electrons are not able to go to the other side. Similarly, the holes are not able to go to this side. So that stops the conduction and you get off state. Now what you do is you reduce it on, off, you go on forever. So that's how the simple diode picture works. Okay, now moving on to the what happens next is that now this is the particular conduction process. Now directly moving to the, I should say, carrier electrostatics, how the electrons now move. That is the part of the assignment now. Now what we are going to deal with is we saw that how electrons move. If you modulate the barrier, the electrons present in the high energy tail, that they are going to go here. The holes present in the high energy tail, they are going to go here, and as a result conduction takes place. And you are just, by applying the potential, you are just modulating this barrier. You are just either moving it up or you are either moving it down. That's it. Now seeing this particular picture, there are certain phenomena in something called as carrier transport. Carrier transport. By carrier we mean electrons and the holes. Electrons and holes, which these are the carriers of current. Because once the, let's say, electron goes from this side to this side, hole goes from this side to this side, because of electron the current flows from opposite direction, IE, and because of hole current flows in the same direction, IH. So you have the overall current in this direction, which is I, that is equal to IE plus IH. All right, so that is the overall current. And that is what we are going to study, how this carrier gets transported. Now you saw that how you can take the electron from this side to this side, but how does that transport take place? It is just like moving a car across a hill. You have understood that there is a hill, there's a car on this side. You want this car to go to this side to this side. You know that you will decrease the hill. You will reduce the hill to this. But here the one fundamental thing is that car already has that energy to go above the hill. It just requires you to reduce the hill. Now the car goes above the hill. The other anti-car, let's call it anti-car, which is the hole, and it goes here. As a result, conduction process takes place. Now, in between, what happens? If the car goes to this side, that means the electron is moving. What happens to the electron? If the hole goes to this side, what happens to the hole? What are the processes taking place? That is what we are going to study in the carrier transport. Okay, so just give me a minute. Let me charge this thing. If you guys have any question, you can just ask me, maybe. Final 30 minutes or yeah.
Sir, on other questions, sir,
Yeah, yeah.
electron spin equal to half. It is experimental or mathematically.
Say it again.
Electron spin equal to half.
Electron what?
Either it is electron spin equal to half.
Spin. Oh,
Yes,
okay.
sir.
That's that it that
Either it
that's
is experimental or
it is experiment.
mathematically true.
It is experimental. But earlier it
Thank you.
was initially it was theoretical, but then it was proved experimentally. But the first they did the experiment, then it was included in the equations, but directly the Schrodinger equation does not include the spin. There is no spin information in Schrodinger
Uh,
equation.
okay, sir.
But that is a deviation from this current topic. That's totally different. If you want to know about spin, you can study something called as spintronics. Right now, we are studying electronics. This is the electronics course. If you want to study about spin, you
Yes,
can study spintronics. This is about electrons as a charge. So we're studying electronics. If you want to study about how the spins, what happens to the spins when the charge conduction takes place, then this is the subject of your concern. Okay.
okay. Thank you,
But
sir.
uh, but anyways, thanks for the question. Okay. So let's move on to the carrier transport. Now, the carrier transport, what happens in the carrier transport? Just a brief overview so that we can directly jump to the questions in the assignment. There, you can directly understand. So, what happens is that uh, that's the list I have made for duplicating. Can just move it here. So, these are the topics which we mostly deal in carrier transport: drift, diffusion, Poisson equation, recombination, electric field, band bending, gradient of the bands. Electric field, band bending, I talked about a little bit. Gradient of the bands, we will talk about briefly. First of all, let's see what happens if you have, let's say, a PN junction, or let's say a simple chunk of a semiconductor. You have a conduction band, you have a valence band. This is simple intrinsic semiconductor. And you have a Fermi level in the middle, something called an intrinsic level. And if you are not applying anything, then you don't have the drift velocity of the electron, because drift velocity is something which is directly proportional to the electric field. And that's why you write drift velocity to be mobility times the electric field, where this is a kind of proportionality constant here. Maybe, but the drift velocity is dependent on the electric field. Now, what happens is that if you're not applying field, you don't have an electron drift. Now, what is the drift? What is the diffusion? Just like in PN diode, PN junction, I showed you that when you are just joined P and N side, the electrons go from this side to this side and holes go from this side to this side purely by diffusion mechanism, because you have more electrons on this side and the Fermi level is higher here. That's why you have more number of electrons here. The Fermi level is above, much more above than the middle. It's near the conduction band, and you have Fermi level near here. So more electrons are here. They want to go from the higher Fermi level to lower Fermi level. Holes want to go from this level to this level. This is a pure diffusion mechanism. Diffusion is a it's a kind of a random process. It's a random mechanism. You don't know how the motion is happening. Just like if you have a gas molecules in a container, and if you just close the container and open a hole suddenly, then gas molecules will start to diffuse through this hole and randomly kind of diffuse through this hole. This is just like that process. We are treating the electrons to be just like molecules, gas molecules, where the diffusion is happening. And we can apply all of those diffusion equations you might have studied in maths or physics, diffusion equations. And diffusion equations, let's say you have maybe you might have studied about thermal diffusion equation, something like if you have the dou T over the gradient of the temperature is equivalent to the conductivity times the second derivative of this. This is the diffusion equation, one type of a diffusion equation. Or you can have dou N by dou T is equivalent to let's say the diffusion constant times the dou square N over dou X square. This is one type of diffusion equation. This is for electrons, this is for temperature. So these kind of processes are similar in nature because of the fundamental nature of the physical process happening. Temperature also diffuses from higher temperature to lower temperature. If you have higher temperature on this side, lower temperature on this side, there's a kind of heat transfer from this side. So similar happens to the electrons. If you have more electrons on this side, the electrons can move from higher number of electrons to the lower number of electrons. Now you have that happens all in a semiconductor. Now you talk about the drift. What happens in a drift is that drift is also a kind of concept where you have drift velocity to be equivalent to mobility times the electric field. But this is a concept that we have been talked a lot about in our classes. And whenever you apply a field to a semiconductor sample, let's say EC, EV, then you apply, let's say, electric field. That means you apply certain potential on this particular sample. What you are doing is that this is a positive potential, this is a negative potential. You're connecting negative on this side, you're connecting positive on this side. Positive potential reduces the potential energy of electrons, and negative potential increases the potential energy of electrons. As a result of that, this particular side of the band goes high, this particular side goes low, and you get something like this. Conduction band, valence band. Okay, so this is the particular level, the Fermi level, or let's say this is the intrinsic level here, intrinsic level of the Fermi level. So this is just the concept I'm talking about. And what happens is that you have the because of applying the negative voltage here and the positive voltage here, you have more energy of electrons here now. When they have more energy, they will go down the hill, and naturally they will be kind of attracted towards the positive end. It's similar thing that whole will go above the hill, because for the whole this above hill is lower energy. Okay, so it's opposite. And once they go into the battery, they recombine and gives rise to the flow of the current, flow of the charges. Okay, so the current overall current flows in the sample. Now, what happens is that if you, let's say, consider the drift. What is the drift here? So how the electron moves in this band. It does not electron does not if this is an electron, it does not directly go down like this. That's not the thing. Electron goes in steps of energies. You know that there are many energy levels here. Just because I told you that there's a distribution of electrons about this, there's a distribution of electrons. So if there's a distribution of electrons, how the electron moves, let's say if electrons here, the electron goes thoda yahan, then down, then there, then down, then here, then down, then here, then down. That's how the electron moves. A perfect picture would be something like this. Electron moves like this, then here, and this is how the electron moves. And when you average out the overall motion and the overall velocity of the electron, you get something called as drift velocity, which is the average concept. You get something called as mobility times the electric field, where this mobility is ne square tau divided by effective mass. This is a average velocity of with which the electron flows in this particular chunk of a semiconductor. But when you if you actually want to know what is the velocity with which the electron is moving, that is actually the group velocity. It's a very fundamental concept, the group velocity. But people don't talk about it. Maybe we will talk about it in a lecture where we will study somewhat about the quantum aspects of the electron. But the drift velocity concept is something like this. Now, if you want to understand, this was drift velocity. Now the governing equations for the drift, for the diffusion, because the current flows due to both of these mechanisms. There is drift, there is as diffusion as well. So whenever the diode is working, there are both functions, mechanisms happening. There is drift happening, there is diffusion also happening. So it's not only the drift is happening or the diffusion is happening. And if you consider the drift, you know that the drift velocity is equivalent to the mobility times the electric field. You can write the Ohm's law in terms of something called as microscopic Ohm's law, which is something J equals to sigma times electric field. Sigma is the conductivity. It's the conductivity. And is equal to NQ mu. I hope it's correct. Yeah, it's equal to NQ mu. And what you do is that you write the current equation for electrons. Current density is the vector quantity. You write for number of electrons, charge of electron, mobility of electron times the electric field plus number of holes times the charge of hole, mobility of holes times the electric field. Oops, this is the overall current, not the current because of the holes. This is total current. So this is the electron component and this is the hole component. And then you write for the diffusion, you write the diffusion current. What the diffusion current is equivalent to, it is equivalent to minus q times dou n by dou x, which is the gradient, which is this basically is the flux, and it comes directly from something called as Fick's law of diffusion, and it's applicable to all of the diffusion processes. And basically there is, I guess there is for the current density, the flux is equal to minus q times dn by dx, but the current density is equivalent to dn times dn by dx. This is the current density, where this dn is the diffusion coefficient. And using the Einstein's relation, you can write it as dn by mu n is equivalent to kt by q. So this was derived by Einstein it comes from the Fick's law, basically from the diffusion theory. And when you write both of the diffusion and diffusion terms for the electron and the holes, you get J overall diffusion current to be equivalent to the diffusion constant for electrons, dn by dx, plus diffusion constant for holes, dp by dx. And this is the overall diffusion current. Maybe there is some sign change here. There is a positive and negative sign here. And it's because the current for the holes flows in the same direction, and for the electrons, if electron is moving like this, the current flows in this direction. So you need to take care of that signs here. And now what you have is that you have a now we talked about the motion, but how this motion takes place is because of the electric field. And now you have the electric field into picture. We're talking about in case of a semiconductor here, or in case of a conductor even. So there is electric field. And now electric field, maybe there can be an external electric field, there can be an internal electric field. Internal electric field can also get developed because of the separation of the charges. Okay, just like if you have a depletion region here, you also have electric field here. Okay, then if you apply a potential outside, that is one more additional electric field. Okay, that's an external electric field. This is internal inbuilt electric field. All right, because there are charges present.
Okay, sir. Okay, sir.
Yeah, so you have any question?
No, sir.
Okay, so okay, then what happens is that if you now, let's say you have a sample like this, you you have electrons, you have holes, and if there is a spatial separation of the charges, let's not talk about electrons and holes. Let's say there's a positive charge, there's a negative charge, and they are spatially separated by some distance x. There will be electric field developed between these two particular charges. Okay, that is going to be from positive to negative. The electric field lines goes from positive to negative. These are the electric field lines, and the electric field lines go into the negative charge. They come out of a positive charge, basic electrostatics, and you can compute this electric field. How do you compute this electric field? Is that if you have two charges, you can simply compute it as kq over distance square minus kq over distance square. You can consider this thing, or you can also use something like del dou dot E is equal to the charge density times the epsilon, which is the sometimes comes from the Gauss's law. And what you can write is that for a simplistic case, you can write this as the gradient of electric field can be equivalent to the charge density times the permittivity. This is the overall charge density. Now let's say the charge density, let's say you represent this thing, let's say you represent, if you have to map the charge here, the charge density with respect to x. Let's say for this positive charge, you represent the charge density like this. This is a positive charge. For a negative charge, you represent the charge density like this for a negative charge. Let's assume a kind of uniform charge. These are not only single positive charges, these are many positive charges. That is the similar picture in a diode where you have positive charges here, negative charges here, and these negative positive charges are Q times Nd. This is Q times Na, assuming the complete ionization of the charges. Then then this is with respect to x, and what happens is that there'll be electric field developed inside, and how this electric field is computed. You know that dou E over dou x is equal to rho over epsilon. Rho will be the total charge. Okay, you can write it as Q times Nd, or you can write it as Q times Na, because Na is equivalent to Nd. The charge is equal on both the sides due to the charge charge balance on both the sides. The charges should be equal. So you can write dou E over dou x to be equivalent to Q times Nd divided by epsilon. You can find the electric field by integrating from x1 to x2, Q times Nd divided by epsilon dx. And if this particular thing is constant, like in let's say a uniform function, then you can write this as Q times Nd divided by epsilon times xn, where this xn is this distance, and this particular distance is xp, where xn plus xp can be it's the overall distance x between the two charges, two sides of the charge distribution basically. And this particular thing is actually a similar thing what happens in a diode. If you have a diode, then there are positive charges over this side, negative charges over this side. So this is a distribution in that particular picture. So you get electric field on this side, electric field to be equivalent to this, or if you use Na in case of Nd, then you can get Q Na xp divided by epsilon. So how do you draw this electric field is you integrate this charge distribution, and you get an electric field something like which looks something like this. When you integrate these particular functions, you get an electric field, because if you differentiate this particular field, you will get it back. You know that there is a let's say there's almost, I should say, if you kind of differentiate this particular curve back, you get this charge distribution. You integrate these curves back, you get this thing. It is just like if you have a delta function. If you have a delta function, you integrate it, you get a unit step function. You integrate it, you get a ramp function. You integrate it, you get a parabolic function. So you integrate with respect to x, obviously. X, x. And you, if you want to go back, you differentiate it. Dou by dou x, dou by dou x, dou by dou x. It's an engineering trick, or it comes from the basics. Just we need to use it. Or simply, if you have any curve, you can just simply integrate and differentiate it. Just like if you have a sine curve, then you know that if you integrate this curve, you get the sine of x. Its integral is minus cos of x. Okay, so you don't get something like you don't get a cos curve, you get minus cos curve. That means something like this. Okay, so you just have to integrate the functions and you get the particular a different function. Or sometimes maybe they're similar function, but you just have to integrate it. Then what happens is that if you know the electric field now, you can compute the potential. The potential is the band diagram. I'm just going from a simplistic picture of space charge. This was space charge to electric field to potential energy to potential profile. That is the band diagram actually. This is electrostatic potential. So you can actually find the potential by integrating the electric field, and when you do it, you get something like this. This is the band. I should show it the opposite way. You get the band diagram something like this, and you can just kind of get one of the bands, and from the potential you can get the N and P concentrations, how they are kind of how their profile is inside the device, inside the diode. And you know that all this comes from this particular equation, this starting point. And that's why there's something called as Poisson's equation, which is this thing is important in kind of electrostatics. So you can also write it as dou E over d dou x is equivalent to rho over epsilon, because you can write it as dou by dou x, dou v over dou x is equivalent to rho by epsilon. This particular thing is electric field. So it's actually a divergence of electric field, but let's assume this is dou by dou x right now. So you get this particular thing, which is something called as Poisson equation. Poisson equation. And with the help of this Poisson equation, you can understand what happens to the energy band diagram when the electron moves. So you have to solve drift, you have to solve diffusion equation, and you have to solve Poisson equation simultaneously to understand what happens to a band diagram in case of a diode. Okay, because every point,
Okay, sir.
yeah,
So, sir, Fourier transformation can be applied in this diffusion equation, sir.
in which equation?
In diffusion equation, sir.
What will you do by applying the Fourier transform? Uh, Definitely, if you have, let's say, diffusion equation dn by dt is equivalent to dn d square n by dx square plus generation minus the recombination, then I don't seem a kind of feasible thing to apply the Fourier transform over this. What that is going to give you, I don't know. But if you have any other equation which is in time domain, then you can use the Laplace transform to solve that differential equation. But just like you have a uh, any other oscillatory problem, simple harmonic motion, d square y by dx square, d square y by dt square is minus y square times omega square times y, then you can solve such equations using the Laplace transform, and you can get the easier solution in a frequency domain. But for applying frequency for Fourier transform to the diffusion equation, it does not make sense. Okay.
Okay, sir.
Hmm. So you need to solve these particular things in order to arrive at the solution. Now what we are going to do, we are going to solve the problem of the assignments. Now it will become a cakewalk to solve the problem. Why? Because we have discussed all of the things. Let's consider problem one. problem 1 and 2 are related, and we have to consider a silicon sample that is maintained at 300 Kelvin, that is room temperature. And we had the band diagram is shown as in the picture. So we talked about much of the band diagram. This is about a silicon chunk, semiconductor chunk. This is the conduction band. This is the Fermi level. Look at the Fermi level. It is flat. So if it is flat, that means it's in equilibrium. Okay, and flat in the sense that there is the concept that one thing is that the Fermi level is constant throughout. That means the overall system is in equilibrium. It's not a non-equilibrium situation. If there is a separation of the Fermi level in systems where the non-equilibrium is there, just like in a diode, when I showed the diode, you didn't ask that what happened to the Fermi level. Fermi level was like this in equilibrium when there was no external perturbation to the medium or external force. This is an equilibrium, no bias applied. Equilibrium means you joined, you waited for some time, you let the charges to settle and move from this region to this region. Number of electrons going from other side to this region are equal to the number of holes. You have a constant Fermi level. If you have non-equilibrium situation, you let's say you apply a voltage, you know what happens to this band. You know that if you apply a forward bias, this will become like this will become like this. But what happens to a Fermi level? The Fermi level is here.
This is not
The,
constant.
sorry?
Sir, this is not constant if uh, Fermi level.
Yeah, in case of non-equilibrium, right? So up to this region, you see that it's flat, but once you draw it in a depletion region, that is the matter of concern. It looks something like this. And you have two separate Fermi levels. This is Fermi level for electrons, this is Fermi level for holes. Okay, so this is, and the difference between the EFN minus EFP is equivalent to the applied voltage. So this is a highly non-equilibrium situation. But this case, what they are showing, it's a equilibrium situation because Fermi level is constant along x. So this is the answer of this question. Simple as that. Now moving on to the other part. Now we have to they are asking about the same question. What is the electric field inside it? You see that he has made he has made the Fermi level like this. There is an intrinsic level like this. This is conduction band. This is valence band. There is an electron. There is a hole. If it is an equilibrium, then you know that electric field you can be computed as rho times epsilon into dx from x1 to x2, and you know that the overall thing is going to be, let's say you can compute, or maybe somehow you can compute the electric field. You know that the electric field is equivalent to the gradient of the energy level. Okay, and if energy level is constant, then you see that electric field is equivalent to zero. Oh no, sorry, that's not the case. Electric field is going to be constant throughout. And my bad, I'm just thinking about some other problem. So what happens is that if you have, let's say, for example, the electric field in this particular scenario, if you have, if you want to compute the electric field by using, let's say, a simple do variation of the energy level with respect to x, what it is going to look like. Since this particular thing is, let's say, varying linearly, that means dou E over dou x is going to be constant as per this particular figure. That means the electric field is going to be flat, is going to be constant, and that is the particular thing here. Okay, and where does this come from is because the force is equal to minus q times the electric field. And you can write electric field to be equivalent to minus 1 over q times the force, and you can write the force as the variation of this particular thing, energy, potential energy variation with respect to the space. And in other words, maybe the simplistic derivation will be You can also write the electric field in terms of the potentials, and you can go back and forth to this equation. It's a simple equation. Now, what happens in question 3? Let's say, let me just check this particular thing. Okay, now you have a semiconductor. It's a three-dimensional semiconductor. You have a cross-section area of uh, let me not. You have a semiconductor. You have a cross-section area. This is 1 centimeter. This is 1 centimeter. The overall area is 1 centimeter square, and you also have thickness of this, which is 0.1 centimeter. Okay, so and your number of electron hole pairs are generated per unit volume by uniform absorption of 1 watt. So let's say you're applying some light of power of 1 watt. There are equal number of electrons and hole pairs generated, and they are uniformly distributed. Uniformly means if you are if this is at x equals to 0 and you are applying light at this particular region, then it's like they are uniformly distributed like this, uniform distribution of electrons and holes. Okay, now these are electrons and these are holes, uniformly distributed. Now, then the wavelength of the light is 630 nanometers. This thing is going to give us energy, I guess. But we're going to solve it. What's the approximate steady state carrier concentration? First of all, what is steady state? Steady state is if you disturb the system and then wait for the system to settle and then study about the system. That's called a steady state. Just like if you have if you disturb the system, it reached some level and then it started to settle at this level. This particular level is called as steady state, and this particular region is called as transient. Transient means where there are changes happening with respect to time. Okay, so steady state is you give some light to the system, then you waited for some time for the system to settle. Okay, to reach the kind of level where there are no variations happening with the time. Then that's called a steady state. It's with respect to the time. If the excess minority carrier lifetime is this, that means tau excess minority carrier lifetime
So
is
there
10 micro.
does not time does not depend.
Sorry.
Steady state. Steady state. Time does not depend, sir.
Yeah, it becomes a kind of steady. It does not vary kind of with respect to time. Then in a steady state, if you are doing any of the experiment or theoretical analysis in steady state, we say that if you have a, let's say, a diffusion equation like for the electrons as something like this, which is generation plus minus the recombination. This means the rate of change of electron concentration is is dependent on this particular thing, is dependent on generation, is dependent on recombination. Now, if you want to solve this in steady state, we assume that it is very long after the application of the external force. So long that with respect to time, there will be no changes. That means we assume that dN by dt is equal to 0. No change of electron concentration with respect to time. When you do it, you solve this diffusion equation in a steady state problem. We get something like G minus R equals to 0. Now, this is an easy problem to solve. It's a simple differential equation for which many solutions exist for different cases. This is called a steady state solution. Okay, so now for this problem,
Okay, sir.
tau equals to 10 seconds, microseconds, sorry. You need to find what do we need to find? Assume, oh God, I'm lost. Okay, we need to find the number of electron hole pairs generated. Okay, we know that the generation is excess number of electron hole pairs divided by the recombination time. Okay, so we need to find this excess number of electron hole pairs, which is equal to generation times the tau. The tau is given, we need to find the generation. What is generation? Generation is number per centimeter cube per second. Number of electron hole pairs produced per centimeter cube per second. And you can write it as in terms of power over energy times the, let's say, the time overall. Oh no, the power over energy times the area. There is a volume basically, volume. And this is basically comes from, you can write power is equal to energy over time. You can write time equals to let's say energy over power. And if you want to write this particular thing as number per centimeter cube per second, this is some time, this is some volume. We replace time with this thing, we replace volume with the original volume, you get the generation. So generation is 1 watt divided by the energy. Energy is Hc by lambda. Lambda is given as 625 nanometer. For it, the corresponding energy is approximately 1.98 electron volts. But you need to convert electron volts to joules. You write 1.98 into 1.6 into 10 to the power minus 19 joules into volume. What is the volume? Volume is how much is the volume? One centimeter into 1 centimeter into
Cube.
0.1 0.1 per centimeter cube. Centimeter cube, not per centimeter cube. Centimeter cube. When you solve this, you get the generation to be 3.1710 to the power 19 per centimeter cube per second. You put the generation back into this equation, you get delta N to be equivalent to 3.17 into 10 to the power 14 per centimeter cube. So these are the excess electrons in steady state. And what do they represent? You already have the total electrons is equivalent to the background electrons plus the excess electrons. If you have a semiconductor chunk, you have the background electron concentration and not. Then you apply light, you generate delta n, and the total n is equal to n naught plus delta n. Okay, so that is the overall kind of concentration. Similar happens to P. P equals to P naught plus delta P. All right, and n naught P naught is equal to Ni square in equilibrium. You can do many things after it, but you just that's what we needed to compute, and the answer is this. This is the generation. This is not the concentration. This is the generation. And now we move to question 4. Question 4 is again easy. We need to find the approximate thermal velocities of the electrons. Thermal velocity. Thermal velocity. Thermal velocity is the velocity with which the electrons move at particular temperature and because of the thermal motion at some non-zero temperature. If you have any sample, whether it's metal, semiconductor, particularly talking, you have electrons going here and there because of the thermal energy, because there is energy in the environment. And this thermal energy is basically kb times the Boltzmann constant times the temperature. If you consider the degrees of freedom of electron, degrees of freedom means electron can go this way, or this way. Then the actual relation is n by 2 times the n by 2 times kt. If n is degrees of freedom, there are 3 degrees of freedom, then the energy can be written as 3 by 2 kt, which is the kinetic energy thermal because of the thermal motion of the electrons. So this is similar to that what happens with the gas molecules. So the gas molecules also have this kind of energy with respect to the temperature, what's called as the kinetic energy. But this is a very simplistic assumption, and now most of the time this thermal energy is uh, mostly it acts like a noise in our systems because we are working at some non-zero temperature, so this velocity is always there, and it kind of gives us a noise level in certain systems. If you want to measure any signal, let's say your signal looks like this, but because of thermal noise, this signal looks like this actually, just like this. You will get an exponential fall, but then you need to fit an exponential to this, and then you will get the actual thing. This particular thing comes because of the noise, and mostly in the electronic equipments, this is the thermal noise. There are a lot of other noise sources, but this is the main source of noise. That's why if you want to see the actual nature of the electron, you go to near 0 Kelvin. You decrease the temperature, because of which the electron's thermal energy reduces. It starts to slowly kind of reduce its energy, the thermal energy. And you can control many things at that particular temperature. That's why most of the experiments in quantum mechanics are done at very lower temperature. And most of the even the quantum computer you might be seeing, that works in, let's say, millikelvin range. The reason is because you want to reduce the thermal energy effect on the electrons as much as possible. Because if the electron is in upper energy state, it can naturally come to lower state. But if it is in this state, because of thermal fluctuations, because of thermal energy, it can go to higher energy state without any control. That's what we don't want. We want to seize this control, so that's why we use the millikelvin temperature range. We decrease the temperature, we freeze kind of the electron motion because of the temperature. Now, what it is saying is that we need to compute its velocity. You know that if the kinetic energy is 3 by 2 kT, then you can write velocity as under root of 3 kT divided by m. So now everything is given. The mass of electron is 0.26 times the, this is the effective mass, and you have to use this value, the 0.26 times the mass of the original electron. So you have to replace this as 0.32 times the mass of the electron. And when you solve it, you get the value of approximately equivalent to 2.3 into 10 to the power 7 centimeters per second. You see, this is the thermal velocity. And just a task, compute the drift velocity of the electron at certain electric field, and then compute the group velocity of the electron at certain group velocity of the electron in certain semiconductor. And you can compare those all of those velocities to see uh, which is more or which is less, in order to understand what is happening with the electrons and with what velocity they are traveling, what velocity is having which magnitude. Okay, so it's a simple thing. And now the question, moving to question number 5. Let's say in a very long type silicon bar with a cross section, you have a long silicon bar, and the area of cross section is, this is 0.5, this is 0.5. That means area of cross section is 0.5 centimeters square, and you have doped it with Na, which is 10 to the power 17 per centimeter cube, and uh, there are excess holes present. Excess hole concentration is 5 into 10 to the power 16 per centimeter cube. Okay, at x equals to 0, this position. There are a lot of holes present. Oh, sorry. A lot of holes present of the order of 5 into 10 to the power 16. We have to assume the mobility of holes this, kT by q is this, tau p is this. What is the diffusion length? Okay, diffusion length is the length which the carrier travels before recombining. If the hole is here, let's say hole will diffuse to lower hole concentration regions. But because electrons are here also, if the hole is moving this way, the electron will be moving this way, and at some distance they will recombine. Electron and hole will recombine. But the distance which both of these carriers travel before recombining, it is the diffusion length. Okay, so that is the concept of the diffusion length. So what we need to find is the diffusion length. Diffusion length can be simply found by diffusion constant times the tau p. I think everything is given in this problem. Diffusion constant is not maybe given. You can compute it by Einstein's relation using dp by tau p is kT by q. Now you got the dp, you have the mu p, you get a you get a diffusion length of the order of 3.6 into 10 to the power minus 5 centimeters. Just you have to put the values of, you get dp from mu p kT by q, put it here, put the tau p is given, I guess. Yes, tau p is given. You compute LP. Simple as that. You get 0.36 as the answer of this question. 0.36 microns. Okay, then this should be, I think, centimeters, or is this meters? Okay, this you get 0.36 as the answer of this question. Just check the units once. Maybe might have messed up with the units. Now the question comes here again. The band diagram is given. Uh, just give me a second. I'll be back. I will just have some water. Okay, so this is the band diagram given and of a semiconductor. And to be particular, this is the band diagram for BJT actually. It's the band diagram of PNP type of bipolar junction transistor. When you sandwich n layer between two p layers, you get a band diagram like this, where the Fermi level is closer to the n side here type here, and it's closer to valence band on these two sides. That means these are two p sides. This is an n side. That's the first question, I guess. At position x1, what type of semiconductor is this? X1 is this position. So at this position, it's an n-type semiconductor. And that's what it is. And at position x2, what is the kinetic energy of electron? Kinetic energy of electron at x2. X2 is this position. There is no bending of the bands. It's a flat band. Okay. And energy is minus q times v. And you know that this particular thing is basically the in the EK space. This is basically the bottom of the parabola. And you know that the EK, the kinetic energy of the electron is h bar square k square by 2m. K is the zero at this particular point, so E is zero. And you can understand it by bands also because the band is flat, so it does not have any kinetic energy at this particular region. It has the potential energy, definitely, but it does not have the kinetic energy. If the electron would have been here, then you could have computed the kinetic energy. Okay, then you could have computed what happens to the electron. Electron will go downhill with certain energy. Then you can compute the kinetic energy and other things. Okay, so the answer is zero. Now, a good question is, for the same case, you need to find the electric field. Now, how do you compute the electric field? I told you that this is like this thing. This is the Fermi level, and you see that this is actually a PNP type of transistor. Let's forget about it. It's a BJT, bipolar junction transistor, where N level is N sandwiched between two P regions of semiconductor. And because of that, there are two depletion regions. One is this depletion region where there are positive charges, immobile ions here, and that's why there is a band bending at these regions. There is another depletion region here. There are two depletion regions. Okay, so here you have the electric field in this direction. Here you have the electric field in this direction, positive to negative. Now you draw the space charge diagram of this. Let's say this is this region, this is this. You draw the space charge, you consider them to be, let's say, uniform. This is positive charge, this is negative charge. This is positive charge, this is negative charge. Okay, here this axis is rho of x, this is x, and this is the space charge diagram of it. And you have to draw the positive above the axis and negative below the axis. That's why it is opposite here. Positive above the axis, negative below the axis. Now you draw the electric field profile. Electric field in this direction, x in this direction. The electric field will be from positive to negative here, positive to negative here. As you go towards this, the electric field will look something like this. Here it will be constant, or rather it should be zero. It's not exactly zero, but let's consider it here to be zero, and here it will be opposite. It will be opposite because it's in this direction, and when you integrate this particular thing, you get this thing. You integrate this thing. That means at this particular point, dou E by dou X is equivalent to zero. What does that mean? If you have, let's say, if you have, let's say, if you are kind of integrating this particular function, there is a maximum change here at this particular position. That is what this particular thing is, particular electric field is showing. That is the exact same thing here. And that means the answer of this question is this thing. There are two regions with this where the electric field peaks like this. So this is the electric field profile of the BJT rather, actually. And then there is another question. The final question is what is the question? Let me just again check. Okay, so what do we need to find is you have a long rectangular direct bandgap p-type semiconductor. You see that whenever you see such long questions in GATE examination particularly, or any type of competitive examination, whether that is JEE mains or JEE advanced, or whether that is GATE or any other, maybe the BARC or any other competitive examination. Whenever there are such long questions, there's always something fishy about it. Either it is having a one line answer or either it is really having a long answer. Most of the times it's having a one line or two line answer. You just have to think, and your brain should be knowing what information to omit. Just like they have given long rectangular bar of direct bandgap p-type semiconductor. Now this information, I don't think this will be necessary in the when you will go to the question, when you will read the question completely. Because once you read the question completely, you should be knowing which information to pick up. Just like they have given long rectangular direct bandgap p-type semiconductor. Okay, this is a p-type semiconductor. Equilibrium hole density is this. That means at equilibrium, this is 10 to the power 17 per centimeter cube. And intrinsic concentration, intrinsic carrier concentration, Ni, is equivalent to 10 to the power 10 per centimeter cube. Electron and hole diffusion lengths are given. This is hole diffusion length as 1 micrometer, electron diffusion length as 2 micrometer. The left side of the bar is x equals to 0, and let's say this is x equals to L. So they have illuminated it with laser, let's say some light, and energy of the photon is greater than the band gap. Okay, fine. So what happens is that if this is electron, it's hit by the photon, it will go above the band gap here. This much is actually the kinetic energy of the electron. This is the band gap. The photon energy is much greater than the band gap. This is the scenario. Excess electron hole pairs are generated only at x equals to 0 because of the laser. Okay, so there are excess electron hole pairs generated here. Somewhere like electrons and holes are generated here. So n is equivalent to n naught plus delta n, p is equivalent to p naught plus delta p. These are the excess concentrations generated because of the irradiation. The steady state electron density is this. This is the electron density at steady state due to laser illumination. Under these conditions and ignoring electric field, the closest approximation of steady state electron density at x equals to 2 micrometers. Okay, so you have to find the, let's say this is some L length L, this is very long. So you have to find the steady state electron concentration at, let's say, 2 micrometers. So you read the entire question and you are like, damn, what I have to do. And what people usually start to do is something like this. They write the continuity equation, the diffusion equation for this. They write these equations and they assume that, let's not assume recombination because they have said steady state. Let's assume this 0 and let's write dn d square n by dx square plus generation. Let's write d square n by dx square to be equivalent to g divided by dn minus rather, and let's write g as delta n divided by tau, delta n divided by tau dn d square n by dx square, and then you have to solve this. How do you solve? You write dn by dx is equivalent to minus delta n divided by tau dn x plus a. This is the constant of integration. You integrated it once. You integrate it again, you get n of x is equivalent to minus delta n x squared divided by 2 tau dn plus ax plus b. This is n of x, the concentration variation along x. Now, what people do once they arrive at this particular thing, now people keep going. They just need to find this particular a, this particular b. Done. Now, what they do, they apply the boundary conditions. We know that n at x equals to 0 is something 10 to the power maybe how much is it, 10 to the power 14, Then they write that n of 0 is equivalent to 0 when this is x equals to 0 plus 0 plus b, and they get b is equal to 10 to the power 14, and they keep going and compute the a again by applying another boundary condition. So this is a very long procedure where you need to solve the equations. But this is a general procedure which cannot be used in a competitive examination, obviously. But people omit the information they usually usually which is given in the questions. Let's say in this question it was given that electron and hole diffusion length is this. So you know diffusion length is the length where the concentration falls to 1 by E of the initial value. If this is if this is exponentially falling some n of x with x, then the length, this is if this is diffusion length L of L diffusion, then the concentration here is 1 by E of the concentration here. Let's say if this is N1, then this is N1 by E. That is the definition of the diffusion length, where the concentration falls to 1 by E of the initial concentration. And and you are totally kind of done with the problem if you know this thing. They have told you to exactly compute it at 2 micrometers, which is the diffusion length. That means this particular thing is the 2 micrometers. And you have to compute the concentration here exactly at diffusion length. And you know that it will be some n divided by E, which is already given. Okay, n of 0. N of 0 is this thing. This is x equals to 0. That means you have to compute n of 0 divided by E. And when you do, let's say, you compute this particular thing, you get 0.037 into 10 to the power 14 per centimeter cube. That's it. That's the answer of this question. And of 0 is already given, 10 to the power 14. So you write 10 to the power 14, or you can write e to the power minus x by L, and that is going to give you the same thing, 1, e to the power minus 1, e to the power minus 2 divided by 2, e to the power minus 1, 10 to the power 14 divided by e. That is the same thing. That's it about this question. And
Yes, sir.
you got the you have any question?
No, sir. Yes, okay, sir.
Or did you got this problem?
No, sir.
You got this problem or not?
I have got it, sir.
Okay,
Got it.
sure, fine. Okay, fine. So the answer of this question is this 0.37 into 10 to the power 14. That means 3.7 10 to the power 13 per centimeter cube. Done. This is a one-step solution. This is a multi-step solution. If you want to go this way, you can go, but it's going to take you 3 to 4 minutes in a competitive examination. This thing is going to take you 30 seconds just by looking at what the diffusion constant, what the diffusion length is. Okay, that's it for this session. That's it. It's almost 2 hours 30 minutes long session. So, anyways, I'll be uploading the lecture. Okay. So if you have any question, you can again I'll give you my mail shazan dot iitb at gmail.com. You can contact me here for any queries or questions. Done. Okay.
Okay, sir. Thank you, sir.
Thank you.
Uh, Thank you, sir. Bye.
Thank you. You have any question?
Upload it, sir. Please upload, sir.
Okay, sure. I'll be
Okay.
uploading it.
Please upload it.
Sure, sure, sure. No worries.
Okay, sir.
Fine.
Bye.
Thank you. Bye
Thank you,
bye.
sir. Bye.